Okay, so today we're starting a whole new topic. We're going to end our look at the world through the lens of the time domain and now start looking at it through the lens of the frequency domain. And so to get from one to the other, we need to enlist a familiar friend, the Fourier transforms, although this time it's a discrete time version of that transform known as the DTFT. Now, as we'll find out through this course, there's actually a couple of different flavors of Fourier transforms relevant to discrete time systems. The DTFT, the discrete time Fourier transform, which is the one we'll be working on today and for the next week or so, which is closest to the continuous time Fourier transform. It's what we would consider the true frequency spectrum of a discrete time signal. There's also a DFT, discrete Fourier transform, which is a discrete frequency version of the DTFT. So it has not just samples in the time domain, but samples as well in the frequency domain. And on a good day, it looks like just a sampled version of the DTFT, although it's only that if you're very careful about how you create it. And its cousin, the FFT, fast Fourier transform, is just a clever algorithm for efficiently computing the DFT. The DFT and the FFT are what are used in computational digital signal processing. So they're very powerful techniques that have moved the Fourier transform and Fourier analysis into a form that a computer can do. But the true spectrum of a discrete time signal, or the true frequency response of a discrete time system, is what is described by the DTFT, the discrete time Fourier transform. And that's the one we're going to engage now. So we're just kind of changing our perspective from looking at signals and systems not as functions of time anymore, as they do when we're looking at them in the time domain, when we're describing them with time domain descriptions, using convolution to compute the system responses, using impulse responses, or unit sample responses, or difference equations and their solutions to determine the analysis of a system. Instead, we're going to move the whole problem, the whole description, everything, the signal descriptions, the system descriptions, and the mathematical tools that we use to combine them to do system analysis into the frequency domain, where the independent axis isn't time anymore, but it's frequency. Why we do that is because it's actually a more natural environment to speak about and to perform the work of designing discrete time systems, discrete time filters. If we think about a filter, we usually think of it in frequency terms. We think of what are the frequencies that I want to preserve? What are the frequencies I want to get rid of? Is there noise that I want to eliminate? And what range of frequencies does it fall into? And so it's that kind of spectral orientation that we naturally have, or that signals naturally occur in, that lead us to want to work in the frequency domain, particularly for the design aspects of discrete time systems. That shows up too in the way we specify discrete time filters. Now we talk about cutoff frequencies or center frequencies, or how much attenuation we get at the beginning of the stop band. So those frequency-based criteria are more the things that we're caring about. And while those aren't the design parameters that we get to control, the things we get to control are the AKs and BKs, the coefficients of the difference equation, in order to achieve a certain frequency response. And so we need to learn the connection between those time domain parameters and those frequency domain performance parameters that we're after. And that's what these transforms give us. When we're speaking about system responses, how we do system analysis, well, in the time domain, we have to either solve a difference equation or we have to perform a convolution, neither of which is a particularly easy thing to do. And it turns out the mathematics of system analysis are actually easier in the frequency domain, where what was once convolution becomes simple multiplication. And so part of the reason we use transforms is to pick up the problem of system analysis, move it out of the time domain into the frequency domain where the mathematics are easier. And as long as getting in and out of the frequency domain isn't mathematically more difficult than actually doing the original problem, then it's advantageous. The other nice thing that we get out of a Fourier transform in a frequency domain look at signals and systems, and particularly of system frequency responses, is we get a very simple connection to predict how a system or discrete time design is going to affect signals of different frequencies. That gives us direct access to the information we need to simply answer that question. That if you give me a frequency response kind of description for my system's behavior, then if I put in a signal of a particular frequency, we can immediately infer what the output's going to be for the system. It will be our original signal at its particular frequency. And if I have a linear time invariant system, the only thing it can do to that frequency component, that cosine or sine, is make it bigger or smaller and phase shift it or time shift it. How much it changes my amplitude of my signal is the magnitude of the frequency response. And the amount of time that it delays, expressed as a phase angle, depending on frequency, is exactly what the angle of the complex frequency response gives me. So if I have this frequency response description, I have a shortcut way of telling you exactly how the system is going to respond to any frequency that I choose to put into my system. That's, of course, if there is no aliasing. As we saw in sampling, the sampling is what we would consider a nonlinear process if we don't do it properly, because it does the one thing that a linear time invariant system is not supposed to do. It changes the frequency of the signal that comes in. And so in the absence of aliasing, though, we can describe systems with frequency responses and treat them as linear time invariant systems. So what do we need to accomplish this? Well, we want a transform that works now on discrete time signals, not continuous signals, so that inherently works with sample data. And Mr. Fourier says, no problem, we'll just take his lovely transform that we learned in continuous time systems and change the frequency element of it from continuous frequency or Hertz kind of frequency to our digital frequency or cycles per sample. And that's sort of what we're going to do. Now, there's a lot of similarity between the continuous time Fourier transform that we learned in 228 and the discrete time Fourier transform, the DTFT. These are the continuous time versions, but there'll be, again, first a forward and an inverse transform. We need mathematical ways to get in and back out of this frequency domain way of looking at things. And when we ask the question, what exactly is this discrete time Fourier transform thing? Well, in comparison to the continuous time version, it's very similar to the continuous time Fourier transform. We would interpret it the same way we would a continuous time Fourier transform. It's still a frequency domain description of a signal. It's a description of how much of what digital frequencies are present in a particular discrete time signal, if we're looking at the spectrum of the signal, or it tells us how much a discrete time system is going to affect signals at different digital frequencies, if we're talking about the frequency response of a system. Same things we could learn from continuous time Fourier transforms for continuous time systems. It's going to be a complex valued function again, so it's going to have j's in it. In most cases, it will have have a real part and an imaginary part. It'll have a magnitude and a phase component. So that's all the same. We'll still plot them with magnitudes and phase versus frequency. Just now, the frequency axis is going to be different. It'll be our digital frequency, our capital F frequency. So that's where it differs from the continuous time Fourier transform. It's also periodic, a periodic function of frequency. So we'll often use a subscript p for the discrete time Fourier transform to remind ourselves that this is a periodic function. And it has a period of every integer value. So remember, capital F is our normalized frequency where we've taken the analog frequency and divided it by the sampling rate. So 1 in digital frequency represents the same thing as the sampling frequency. And we saw when we did sampling theory that we got copies of our spectrum kept repeating and recentered on every integer multiple of that sampling frequency. So the DTFT version of that has still the repeating spectrum, but now the repeats happen at every multiple of 1. So at 1, -1, 2, -2, and so on. And again, our independent axis now is digital frequency, cycles per sample, or digital radian frequency, radians per sample, not cycles per second or radians per second. It's our digital normalized frequency, capital F. And this properly describes the frequency content of a sampled data, a discrete time signal, not the continuous one. And in fact, this periodicity is what comes from the fact that we have a sampled signal. Now, how do we get to that transform? We can't just simply take the Fourier, the continuous Fourier transform and replace little f with big F, although close. To derive the actual expression, we can start with the familiar territory, the same kind of argument we were making with how we do sampling in the model that we came up with for sampling, where we said we take a continuous time signal and multiply it by an impulse train, where that impulse train had a unit magnitude impulse happening every t sub s, so every sampling instant, and multiple of those. And when we multiplied these two together, we got a train of impulses that were now weighted by the original functional value of our signal that were occurring at the instances that these impulses fired. And so we had this, what was essentially a continuous time, notice a continuous function of t, that kind of representation of our discrete time signal. And it took sample values of the input, the continuous time signal, at those sampling instances, and times t sub s, used those to scale impulses that happened at those instances, and had some infinite number of them if we had an infinitely long signal. Now, to approach what is this discrete time Fourier transform going to look like, we're going to want to transform that continuous time sampled data signal. So if this is our model, we'd like to take the Fourier transform of that. And we can sneak up on that using some principles and properties of the continuous time Fourier transform. If we define our time function, our continuous time function x of t, and say whatever that function is, it has a continuous time Fourier transform, capital X of little f, we know that from the properties of continuous Fourier transforms that if x of t has a Fourier transform x of f and y of t has a Fourier transform y of f, if I add those two signals and then take the Fourier transform, I should get x of f plus y of f. That's that Fourier transforms are a linear operation, therefore they obey the additivity property. Likewise, they obey full superposition. If I scale x or y by some scalar coefficient a or b, I equally scale their Fourier transforms because, again, they are homogeneous. They are linear. Fourier transform is a linear property or linear operation. We also have seen that the Fourier transform of a shifted delta, a delta of t minus alpha, is e to the minus j 2 pi f times alpha. Or more simply, we know that from the time shift property of Fourier transforms, if we know the transform of some time function, when we delay it in time, we multiply it by this factor, e to the minus j 2 pi f times the time delay alpha. All right, well, here's the continuous time description of a discrete time signal, and we'd like to know what's the Fourier transform of that look like. Well, Fourier transform of a delta function, a delta of t minus n t sub s, is e to the minus j 2 pi n f times n t sub s, the delay. X of n t sub s is just a scalar constant, so that's going to multiply the Fourier transform of the shifted delta function. And if we add up an infinite number of time functions, we add up an infinite number of their transforms. because it's just additive. And so this then would be sort of the continuous time Fourier transform equivalent of our discrete time signal model as a continuous time signal. And that's our starting point for how we're going to define the discrete time Fourier transform. It's kind of this, but not exactly. If this is our input signal, this we said is its Fourier transform. Well, we can simplify this a bit more. The continuous signal taken at instances n t sub s, well, those are just the sample values we're extracting. Those are the x sub n's. We want this in terms of our new digital frequency, capital F. Well, that digital frequency is little f, the analog frequency divided by the sampling frequency. The sampling frequency is the reciprocal of that sampling interval, t sub s. So little f times t sub s is the same as our capital F. And we have a little f and a t sub s in our transform here. So we can make that substitution along with saying x continuous x of n t sub s is the same as our discrete x sub n sample values. We can come up with our new flavor, our new form of the Fourier transform that's appropriate for discrete time signals. X sub n e to the minus j 2 pi n times our capital F, our digital frequency, summing that over all n. And when we do the summation over n, the n's go away, leave us behind a function of capital F, the digital frequency. And this is the definition for the discrete time Fourier transform. If x sub n is some discrete time sequence with integer indices, then if we define x sub f as the discrete time Fourier transform of x sub n, it's computed with that formula. It's the summation over all n of x sub n e to the minus j 2 pi n capital F. And this does result in a periodic function, so we'll use the little p subscript to remind us of that. And this then is the discrete time Fourier transform, the DTFT. It's a continuous spectrum, so we're using parentheses for frequency here of this because it is a continuous spectrum. It exists for all values of f, not just at particular discrete ones. It is, however, periodic and repeating, which is why we put our little subscript p in there, and the period is 1. Now, so that's our new transform. Before we use it, though, we kind of need to understand its limitations. We need to understand when can we use it and when can't we use it. When does it exist? What class of signals can we put into the transform and get a valid answer to? Well, give me an x sub n. It has a valid result of this summation. It has a valid and unique discrete time Fourier transform if this summation converges, right? If we get some finite sum out of this, then we have a closed form solution we can use for the discrete Fourier transform. Okay, so we need this summation to converge. Let's look at our factors. Here we're just summing up an infinite number of them. Okay. X sub n, well, that's our signal. So we clearly want it to be somehow bounded, probably. And then we have this exponential term, e to the minus j 2 pi nf. So we want this sum to converge. We want it to have a finite value in the sum. So we could ask ourselves, do any of these factors automatically make it converging? Is this something we don't have to worry about? And x sub n, well, that's going to depend on the signal. But this e to the minus j 2 pi nf, we might ask, does that already help? Because, we've got a negative exponent going here. So maybe this could be helpful for making sure that we converge in this summation. Well, let's check that out. And so the question that I'm posing is, if we have this factor in the discrete time Fourier transform, this e to the minus j 2 pi n capital F, does that help make my signal or the product of that with our x sub n converge? Does it help make things smaller? So we want to investigate how big is that, and does it get bigger or smaller with n, or with f for that matter? And so you've probably seen this argument before, or maybe you recognize it right off the bat, that is a complex exponential. So we're asking the question, what's the size, what's the magnitude of that? Well, hard to interpret maybe in that exponential form, but the Euler identities let us break it up into its real and imaginary components. E to the minus j anything is cosine of that thing, in this case 2 pi nf, and we have a minus j times sine of 2 pi f, 2 pi nf, minus because we have the negative sign in the exponent. If this was positive, we'd have a plus j sine 2 pi nf. And so we have a complex summation there where we have the real part here, we have an imaginary part over here. So that magnitude's going to be, right, the square root of the real part squared plus the imaginary part squared, and the square root of those, which then is the square root of the real part was a cosine 2 pi nf. We'll square that. And the imaginary part was a negative sine 2 pi nf. And when I square that, now certainly the squaring makes the negative sign go away, and we can bring that square inside. And sine squared plus cosine squared of anything is 1, right? And so this has a magnitude of 1, no matter what n or f is. And so it's not going to be of any value at all for making our Fourier transform converge, which is unfortunate, but not necessarily a problem. So that doesn't help. That means everything is dependent on x sub n. So if we want this Fourier transform to exist, x sub n has to basically be a converging function. And we can tell that it is by testing whether or not it's absolutely summable or not, just like we did for unit sample responses. So if x sub n is absolutely summable, meaning its absolute value summed over all n gives some finite value, something less than infinity, then the Fourier, discrete time Fourier transform, this summation will exist. We'll get a closed finite solution out of it. That being said, that's actually a little bit overly conservative. There are still some signals that don't qualify technically that way, that are not absolutely summable, and yet they still have valid discrete time Fourier transforms. And the classic example is a unit step. Unit step is, goes to 0 till n equals 0, then it goes 1, 1, 1, 1, 1 forever. So we sum up that infinite number of ones, we get infinity. So it's definitely not absolutely summable, but it does have a valid discrete time Fourier transform, as it turns out. So if a signal is absolutely summable, then for sure we know its discrete time Fourier transform will exist, always. If it's not absolutely summable, its discrete time Fourier transform might exist. And the key to whether it will or not will be if it's growing at an exponential rate, it will not have a discrete time Fourier transform. That summation is going to blow up to infinity. If it's not absolutely summable and it does have a valid discrete time Fourier transform, well, the DTFT is likely to include frequency impulses, delta of f functions, which are okay. But if we do have an exponentially growing time function, its discrete time Fourier transform won't exist. That summation won't converge. Okay. A couple things about our discrete time Fourier transform. First, again, it is periodic. We saw that in sampling theory. It's periodic with a period of 1 because 1 represents the sampling rate. We can prove it very simply using the definition of a discrete time Fourier transform. If it's a periodic function with a period of 1, then if I compute the discrete time Fourier transform of some function of f plus 1, I should get the same answer as the discrete time Fourier transform of the same function of f. So we move ahead by a period and should get the same answer. So we simply take the definition of the discrete time Fourier transform and plug in f plus 1 in the place of capital F and try to simplify it. Well, this exponential we can break up into two components, the e to the minus j 2 pi n capital F multiplied by e to the minus j 2 pi n times 1. And what is this e to the minus j 2 pi n times 1? Well, as we just saw, that's cosine 2 pi n minus j sine 2 pi n. N is an integer, so that's a cosine 2 pi, 4 pi, 6 pi, 8 pi, minus j sine 2 pi, 4 pi, 6 pi, 8 pi. And cosine of any integer multiple of 2 pi is 1. And the sine of multiples of 2 pi are 0. So this evaluates for any n, this is always 1 plus j0. So it's just multiplying by 1, which gives us back exactly our original definition of a discrete time Fourier transform. So easy to prove that it's going to be a periodic function and it's going to be periodic with a period of 1. And so doesn't matter what kind of signal, as soon as we sample it, as soon as we have sampled data, discrete time signals, its frequency spectrum has to be periodic. It's unavoidable. Now that Fourier transform, just like the continuous time version, is typically going to be a complex function of frequency, of capital F frequency. So it'll have a magnitude and phase, which we can write in either kind of form as magnitude and angle or magnitude e to the j angle. We could break it up into real and imaginary parts, and sometimes we'll need to do that if we want to simplify things. And we know the relationship as we just used it is the magnitude of the complex function is the real part of the complex function squared added to the square of the imaginary part with the square root. And the angle part of this complex function is, well, if all else fails, we can always use an inverse tangent of the imaginary part, which could be a function of frequency, divided by the real part as a function of frequency. And we just need to take some care about keeping track of which quadrant we're in with these angles, depending on where your plus and minus signs are in your real and imaginary parts. It'll determine which quadrant this angle is actually in. Now, most of the signals we're going to be transforming are real valued time sequences, meaning our x sub n has real valued. Think of a sensor connected to a sampler. So we're getting, or connected to an A to D converter, and we're getting temperature readings every so many seconds. Those are going to be real valued information. There's not going to be any J's in our original time domain data. Well, it turns out if we take the Fourier transform of real valued data, it has certain consequences on the symmetry of the discrete time Fourier transform, just like it does the continuous time one. If your time function is real valued, its Fourier transform magnitude has to be even symmetric around f equals 0, in this case capital F equals 0. And because it's periodic, that means it's also going to be even symmetric around f equals 1, f equals 2, f equals 3, and so on. Interestingly, because of the periodicity, it's also going to be even symmetric around every multiple of the Nyquist rate, 1/2. So 1/2, n1, n1.5, n2, and so on will be even symmetric. The phase as a function of frequency of a real valued time sequence, however, has odd symmetry around n equals 0 and n equals 1 and n equals 2 and all those multiples. And again, also around the Nyquist rate, 1/2, 1, 1.5, 2, and so on. So if you have a real valued time domain signal, which usually we do, we'll expect to see the symmetry, even symmetric magnitudes, odd symmetric phases. Now, if you have even or odd symmetry in your time function around n equals 0, then that will impose additional symmetry requirements on the discrete time Fourier transform. Namely that if your x sub n is both real valued and is even symmetric around n equals 0, its discrete time Fourier transform will be a completely real function. There'll be no j's in it, no imaginary part at all. And if I plot just this real function versus frequency, that real function will be even symmetric around 0 and the Nyquist rate and every multiple of those. The angle, because it's a real valued function, the only angles that we could possibly have when we're thinking of complex function angles is either 0 phase for a positive real value, or we need to have a negative, be on the negative real axis, which is at plus or minus 180 degrees, plus or minus pi. So if we think of our axis, our real and imaginary axes that are perpendicular, we're either on the positive real axis with 0 phase or the negative real axis with plus or minus pi phase. We still have the original symmetries we should have for the magnitude and phase of the discrete time Fourier transform because x sub n was real. These other symmetries, the being real valued and even symmetric around 0 for the real valued function, are distinct from these two requirements. If your time function is real valued but odd symmetric around n equals 0, then we get the opposite case. Your discrete time Fourier transform will be purely imaginary, be all j's, no real part. And so that if we plot that function of frequency versus frequency, that will have odd symmetry around f equals 0. And because it's purely imaginary, it's got to be along the imaginary axis. So the only two possible angles it could have is plus 90 degrees or minus 90 degrees, or plus or minus pi over 2 if you're using radians. Now, still has the same symmetry for the magnitude and phase. It still has to be even symmetric for magnitude, even while it's odd symmetric around f equals 0 if I just plotted the function itself. So that just tells me that part of this function goes negative on one side and positive on the other. But when I plot the magnitude, it still looks, we flip it up and it looks even symmetric. So it can be all these different symmetries simultaneously. Okay, let's go through a couple of computation examples so we can see how we apply it, how the computation works. It's a summation, so we're going to need some geometric series summation formulas. We're going to need some other properties of things like impulses and cosines and sines, depending on what we're trying to compute here. But let's take the very simplest example to start with. What's the discrete time Fourier transform of a single unit sample at n equals 0, a unit sample sequence, a delta sub n sequence? So we just simply plug that into our discrete time Fourier transform summation. Its Fourier transform is the sum over all n of x sub n e to the minus j 2 pi n capital F. Well, I only have 1 at n equals 0. So when I plug that function in here, this summation is 0 everywhere for every n except n equals 0. And at n equals 0, this delta sub n becomes 1. So the whole summation degenerates to a single value, 1 e to the minus j 2 pi for n equals 0. That's e to the j 0, which has a value of 1. And so just like the continuous time Fourier transform of a continuous time impulse, The discrete time Fourier transform of a discrete time unit sample is 1. And so we have right away this a stark duality between time and frequency because of their reciprocal nature. The narrowest possible thing in the time domain gave rise to a completely wide unit value everywhere in the frequency domain. Or another way of looking at that is that single unit sample contains every possible frequency that there is, which gives some credence to why we use a unit sample response as our way of characterizing a system's behavior. It's like we're putting in a signal that has every possible frequency in it, built into it already. Our second example is going to be a little contrived, but it's going to give us a rather curious result. So bear with me on this one. Our time signal here is not a causal signal. It's a non-causal signal. It has 1/2 at n equals -1, 0 at n equals 0, and plus 1/2 at n equals 1. And we want to plug that signal into our discrete time Fourier transform formula. Again, I only have, in this case, 2 terms where for n equals -1 and n equals +1, and those have magnitudes of 1/2. I have nothing for n equals 0. So when we expand out the summation formula, we only get this 1/2 e to the minus j 2 pi times n, which is 1 minus 1 for this term, and plus 1/2 e to the minus j 2 pi n equals 1 for this term. If we get rid of the double negative here, we see we have 1/2 e to the j 2 pi f and added to 1/2 e to the minus j 2 pi f, which you should immediately recognize as a cosine of this argument, 2 pi capital F. Now, this is a cosine, it's not a cosine 2 pi ft. This is not a time-varying cosine. This is a function of frequency that happens to have the shape of a cosine, which came out of this rather strange-looking signal. So how would I plot that? How would I deal with that if I wanted to show the magnitude and phase of this function? Our function, our xp of f of capital F, was a cosine 2 pi f. And I want to plot that. Let's just plot that first versus capital F frequency. Oh, did you notice? It's a real valued function. There's no j's here. Well, our original function looked like what? Here's our n, here's our x of n, and it was 0, 0, 0, 0, 0, 0, 0, 0 there, and then it only had a 1/2 and a 1/2, which is even symmetric around n equals 0. And so as we advertised, we got a real valued Fourier transform out of that. Okay, which we can plot as a function of frequency capital F. Let's see, it's a cosine, so it's going to start at 1, it's going to wiggle back and forth and wiggle back and forth with some fixed frequency, and it's going to come out here at 1 and come up here at -1. Now, typically we can't plot a discrete time Fourier transform as directly as a function of frequency, usually because it is a complex valued function. So normally we would plot the magnitude versus frequency and the phase angle versus frequency. And how would we treat this one, even though it's real valued? Well, we would do this, we would plot the magnitude as you would expect, right? We follow this when it's positive, and when it's negative, we flip it back up. And when it's positive, flip it back up and just have these looking like a full wave rectified version of our signal. There's our 1 again, and our -1. And for phase, well, in this range of frequencies, our x sub f was positive and our magnitude was positive, and so we don't have any phase on that. It's a positive real value. In this next segment, the value of the function is actually negative, but I plotted the magnitude as positive, so I need to get a minus sign out of the phase. I need to show that I'm on the negative real axis. So for that, I'm going to put in a minus pi phase in there. And then in the next segment, we go back to 0. And in the next segment, we've got another negative component. So we need to go minus pi again, and so on. And on the opposite side, well, here I've flipped my sign around again. So I need a -1 out of my phase. And for a reason that I'll explain in a moment, I'm going to go to plus pi for that side. And then over here, this is positive, so I need a 0 phase. And then this one's negative, so I need that plus pi phase again, and so on. So we use the phase term to get the -1 for our actual Fourier transform value when we're plotting it with the magnitude and phase form. Now, why did I choose plus pi over here and minus pi over here? Well, the choice was arbitrary for one of them, but once I chose this one to be minus pi, this one had to be plus pi because, again, the magnitude should be even symmetric around n equals 0, and it needs to be odd symmetric, around f equals 0, and must be odd symmetric around f equals 0. Okay, so that's why we chose that approach. Let's go back. Yeah, question.
I had a question. So if you had picked the other phase, like the one on the positive x-axis to be pi, then the parts where x is less than 0 would have to be negative pi.
Right. If I had chosen to make these ones plus pi, then I would have had to chosen to make these other ones minus pi to keep the right symmetry. Okay, let's do one more real quickly. For the next one, we're going to need an infinite geometric series summation, and one that we've run into once already and we'll keep running into. The sum from 0 to infinity of some exponential, something a to the n, as long as n is fractional, its magnitude is less than 1, is 1 over 1 minus a. A finite geometric series from 0 to n minus 1 of the same kind of exponential term turns out to be still 1 over 1 minus a, but minus a to the capital N in the numerator. We can put that to use to come up with the discrete time Fourier transform of alpha to the n u of n, a causal exponential term. So that's 0 for n less than 0, and then it's a squared, a cubed, and decaying as long as the magnitude of alpha is less than 1. If we plug that into our discrete time Fourier transform formula, first I can get rid of all the negative n values because of that u of n being causal. I'll just start my lower limit of the summation at n equals 0 to take care of eliminating the negative part. U of n is 1 after that, so I can drop it out of the expression. And I have the sum from n equals 0 to infinity of alpha to the n e to the minus j 2 pi nf, which I can rewrite, since these both have exponents of n, I can rewrite this as alpha e to the minus j 2 pi capital F, all raised to the n power. And that's a to the n summation, which we know the closed form answer to. It's 1 over 1 minus whatever we had here raised to the n power, in this case, alpha e to the minus j 2 pi f. That's definitely complex. The numerator's real, but the denominator is complex, has a real part, and has an e to the j term, which has a root part, a cosine part, and an imaginary sine part. If we wanted to plot the magnitude and phase of this, we would break it up into its real and imaginary components. So using the Euler identity, and then compute the magnitude. Well, the magnitude of the numerator is just 1. The magnitude of the denominator is the real part, which is the 1 minus a or alpha cosine 2 pi f, quantity squared. Add it to the imaginary part. Don't bring the j along, just have the alpha sine 2 pi f and square those. If I FOIL out or square this polynomial here, I'm going to get the first term squared plus double the product of these two plus this term squared. And after I do that, I have parallel terms here, alpha squared cosine squared 2 pi f and alpha squared sine squared 2 pi f. So that's alpha squared times cosine squared plus sine squared, which is just 1, which leaves me behind just alpha squared. And take the square root of that, and we have a closed form expression as a function of frequency for the magnitude of x sub f. For the phase, we need the angle of the numerator. Well, that's a real value 1, so that angle is 0. And we subtract off the angle of the denominator. So we subtract off the inverse tangent of the imaginary part, alpha sine 2 pi f, divided by the real part, 1 minus alpha cosine 2 pi f. And that we can also plot that versus frequency. And here's what they would look like. That magnitude term, this 1 over square root term, looks like this. It peaks up at 2 at f equals 0, dies down, and then at f equals 1/2 turns around and goes back up. It's periodically repeating with exactly the same shape, even symmetric around f equals 0, f equals 1/2, f equals 1, and so on. This phase term, this minus inverse tangent, is odd symmetric around f equals 0 and around the Nyquist rate. And as you see, it passes through 0 here at f equals 0 and goes negative and then turns around. And again, this pattern would keep repeating over and over, infinitely long in both directions. Okay, so that's a couple simple examples of how we would compute the discrete time Fourier transform. Next time we'll come back and talk about, all right, how do we make use of this? How do we deal with finding transforms of more complicated signals? And then what can we do with it once we have that? That'll be the emphasis for then.